We'll go to the lecture 11. We have 2 lectures left, and both of them, one is the continuation of the other one. So there will be 1 tutorial for the 2. So we have 2 lectures left and 1 tutorial. Lecture 11. Finite state machine. This is the title of this lecture, or FSM. This is a very interesting topic, and of course the FSM are special sequential circuits. So we will be using the flip-flops to design them. In addition to flip-flops, we will use combinatorial circuits. So you will use the flip-flops and the gates, or you can use as well the multiplexers. But it is a sequential circuit because it will have flip-flops, it will have a clock. So, and then you will understand hopefully later on why do we need to have gates in this type of circuits. So from the name of the circuit, finite state machine, so it has a limited number of states. So we know exactly, a counter is a very good example of finite state. So we know that if we have a 3-bit counter, we know it goes from 0 to 7. We know that if the current state is 0, the next state, when we talk about states, is the outputs, yeah? If the current output is 0, 0 is 0, 0, 0 with 3 bits. We know that the next one should be 0, 0, 1. If there is no reset, if there is a reset, it will stay 0. So we know exactly what are the states, and this is why we call it finite state machine. So we know what are exactly the states and what should be next. Can you give me an example from the real life example where in a circuit or in where it's considered as a finite state machine, so we know exactly what should be the next state? Can you think of an example?
I think maybe, for example, the queuing system when you go to the bank or something.
The bank?
The queuing system, for example, if you get like a number, so you know that when someone gonna press the button, it's gonna be the next customer, the number of the next customer.
Yes. So this is yeah, a queuing system. Yeah, this is a good case. One in the roads, the traffic lights. The sequence, right, of traffic lights. We know if it's red, what will come next, and we know what if it's green, what will come next. There is as well the lift, elevator in the shopping malls. You know that, if you are in the first floor, what are the possible combinations that you can get? What could be the possible next state? And it's a limited number of states. We know exactly how many floors are there. And then depending on what the user enters, so there are inputs from the user, we know exactly what should be the next state. So of the states. So this is why it's called finite state machine. And so this is why we need to know what is the current state, and we need to know what should be the next state based on the coming inputs. Do you understand? So we'll show you in this lecture how to design this type of circuits. And these are sequential, and we use flip-flops in this. Right. This is what I mentioned here. So we could work with D flip-flops, or we could work with JK flip-flops. We will do both of them. In this lecture, I will just show you the flip-flops, but in the tutorials, we will use JK. I can show you an example as well with JK here, but it's not in the slide, so we can show you an additional example. But we can work with both. You can decide which one you want to use. But we don't mix. You use one, you continue with one. And one very important thing when we design this type of circuit is the excitation table, or to get the excitation logic. The excitation logic is basically the combinatorial part of the circuit. So we know that we need to use JK flip-flops, and we know that we need to use as well gates. But how do we connect those gates? How many gates do we need? How do we connect them to the flip-flops and so on? How do we connect them to the inputs of the circuit? To do this, we need to find the excitation logic. And to find the excitation logic, we need to find the excitation table. You know what is a truth table. So the excitation table, you will see that we will inverse the roles of inputs and outputs for the reasons that I already explained, and I will explain them further. Right, so we'll come back to the excitation logic next. But first, we have two types of those finite state machines. We have the Mealy machine and we have the Moore machine. There is a small difference between them. You will see that in all of them, we'll have like three components, three main parts. We have the combinatorial logic next state. We call it combinatorial logic next state. So this is combinatorial. So this will consist of gates. And then we have the state register. The state register is basically like what you save the current state, so we know what will be the next one. And this will be flip-flops, D or JK. So here we will have the flip-flops. Of course, depending on the circuit that you want to do. If the circuit has only one output, then you need just one flip-flop. It has, like we say, a counter with 3-bit counter. In this case, we will need 3 flip-flops because each flip-flop will give us 1 bit. So now the number of flip-flops to be used will depend on the circuit itself, how many outputs you have. And then in the Mealy machine, outputs, so we will have the inputs of the circuit. So those are the inputs. We will have the outputs. And then this is the internal architecture. So inputs, outputs, and then the inputs in the Mealy machine, the inputs, we use them again here in this block. Do you see? So inputs, in addition to go to the first block here, the combinatorial logic for next state, they are fed as well to the output logic, the combinatorial output logic. We have like 2 combinatorial logics, one in the beginning and one at the end. And then in between, we have the circuit. Sometimes this one, it's nothing. I mean, you just connect the outputs and that's it to the output. This will be the output, the final output. You will see some examples later on. And then the Moore machine, those outputs are not fed here. So this is the main difference. But again, we have the 3 blocks. Again, those are flip-flops, and those are combinatorial. Those both here are combinatorial circuits. When we say combinatorial, sometimes it's just simple gates, 1 gate, 2 gates, and so on. That's it. Right. This is in general. We have two types. Now we'll show you how to design those finite state machines. To do this, as I said, one very important thing that we need to find is the excitation table. And this excitation table will depend on which flip-flop you are going to use. So if you are going to use the flip-flop, you will come up with a different excitation table than using a JK flip-flop. What does this excitation table do? So for example, if, as I said, or this excitation table, it will help us to get what? As I said, if I use the D flip-flop, for example, and we know that we have limited number of states. So if the current state is 0, and I know that the next one should be 1. So current, next state should be 1. So the question that I ask myself here, what should I have on D to get this next state to be 1? I know the current state. I know what should be the next state. So now the question is, what should I do on the input D of the D flip-flop to force the next state to be 1? Do you understand? And this is very important. So let's switch to the right. I know that for D, Qn plus 1. This is the for D flip-flop. If I have 0, 1, 0, 1, 0, 0, 1, 1. So for D, if D is 0 and the current state is 0, what should be the next state for D flip-flop?
0.
0. This is a normal truth table for D flip-flop. If it's 1 and the current state is 1, it should be 1. We know that Q follows D. If it's 0 and then the current Q is 1, then the next one should be 0. If it is 1 and then the current one is 1, then it stays 1. This is the truth table for D flip-flop. Now, when I try to find the excitation table of the system, let's say it consists of 3 D flip-flops. So this is D flip-flop. I need to use the excitation table for the D flip-flop to find the excitation table for the system. What is the excitation table for the D flip-flop? Instead of starting with D now, I will put Qn, and then I will put Qn plus 1, and then it will be like D will be the output. And then those are the possible combinations, right? This is the excitation table.
The last one should be 1, doctor, not 0.
Yes, 1. Good. Excitation table for D flip-flop. Now, this is what I'm asking myself. The current Q is 0. And I know the next Q should be 0. What should I put on D to get 0? Or
0.
to get 0. So I need to put 0 here. I'm inversing. Do you see the input and output here when I do the excitation table? Now, if the current Q is 1, and I want the next Q to be 0, then I will put 0 here on D to get the next Q 0. If the current Q is 0, and I want the next Q to be 1, I need to put 1 here. And then I need to put 1 here. Basically, this is Qn plus 1. We say D is equal, or Qn plus 1 is equal D, or the other way around, right? The excitation table for D flip-flop is easy. Now I'm going to go to the excitation table for JK. I will start with the normal truth table for JK. Qn plus 1. 0, 0, 0, 1, 1, 0, 1, 1. So if I have, so what should we get for the JK 0, 0?
Qn.
Yeah, this is a normal truth table. Yeah, so here is Qn. Good, no change. And then here is a reset, right? Next.
0.
A reset, 0. And then here is, sorry, yeah. What did they do here? 0, 0, 1. Sorry, I just messed things up. So 0, 1, 0, 1, 2 zeros, 2 ones. So 0, 0, 0, 1, 1, 0 is 1, and then here is Qn bar. So this is what we know about the JK. Right. Now, excitation table for JK. This is truth table. JK flip-flop. Now I want to do the excitation table. Qn, for the excitation table, I will use, so J and K will be like the outputs now. Then those are the cases that we will have. And then I will ask myself, now I have Q is 0. And I want the next Q to be 0. So I know that the next Q should be 0. What should I do on J and K to get 0?
0.
I can do, pardon, 0, 1, right?
You could do 0, 0 or 0, 1.
I can do this one, both of them, one of them. I can do 0, 0 or 0, 1. So basically I can do 0x, where x could be 0 or 1. So I can just put 0x here. So K could be 0, could be 1. Okay, good. And then next one, 0, the current state is 0, and I want the next one to be 1. So I can do a toggle, right? Do you follow?
So is either 1, 0 or 1, 1.
So I can do 1, 0 or 1, 1. So if I do 1, 0, I will force it to 1. It's a reset. Or I can do 1, 1. I will get a toggle, which will invert the 0. So I can do 1, 0 or 1, 1, which means I can do 1x. Right? Now, current state is 1. And I want next one to be 0. So basically, I can do a reset, right? I can do 0, 1, or I can do another toggle, right? 1, 1, which means I can do x1. Zero, 1 or 1, 1. If I do this and my current state is 1, I will get the next one 0. And then we will use this later. So those two tables are very important, for one for the flip-flop and one for JK. Those two tables, we will use them to find out our logic, or excitation logic. 1, 1. And I want the next state to be 1. So I can do no change, right? Or I can do a set 1, 0. So which means basically I can do x 0. Oh, sorry. I don't know how did we get this one. X 0. And this is the excitation table for JK. This is the excitation table for JK flip-flop. So if I switch back to the slides, I put them here, and this is how you see those are with different numbers. So, but this is what I was explaining, yeah? 0x, 1x, x1, and then x0. And here it's 0, 1, 0, you know, the tables that I've just showed you. I think you have the correct ones on the PDF. Now, of course, we will use this table if we have one flip-flop, but if you have more, we will use those tables as well and apply them to the other flip-flops. So if a system has n flip-flops, then I need an excitation table that will have 2 power m rows in the excitation table. So this is the ones that we are going to use. So again, the excitation table for the full system or for the full circuit, it will depend as well on how many flip-flops do we need. So we'll have examples later on, yeah? Is this clear? How did we guess the excitation table, which we are going to use later? So basically, this is very important what I put here. As we know, if we know the current state and we know what should be the next state, so what are we going to do on the inputs D or JK to get what we want? This is how we construct those excitation tables. Right. Now I'm going to show you the steps, how to design from A to Z. So we have four steps. The first thing that you need to do is to know your states, how many states you have, or basically how many outputs. When we talk about states, is the output. So if I say I have a 2-bit counter, 2-bit, so I will have, those are the outputs, 0, 0, 0, 1, 1, 0, 1, 1. So those are my states. So when you start designing the system, you should know what are your states. If you design a traffic light, how many inputs you should have, outputs you should have? You should have 3, right? Because we have 3 lights. So 1 input for each light. So 1 will be controlled by each flip-flop. So you will have a circuit that has 3 outputs. 1 will go for each light, and then you control the lights. So when do you need 0, 0? When do you need 0, 1, 0? When do you need 1, 1, 0? And you may not have all the states, you know, like in a counter or opposite. You can have just 2 states or 3 states. Even with 3 bits, you may have in your circuit just those are the valid states. For example, you don't need the other states. And this is, so your circuit will have 3 states and you will need 3 bits. It doesn't mean that if you have 3 bits, you will need to use all possible cases. No. For a counter, yes, we use all possible cases. I may ask you to design a counter that counts, that increments by 2. In this case, you will not use all possible cases. And you can design this counter. Do you understand? So I can have, so start 0, 0, and then the next state will be 0, 1. If I use 2 bits, and then that's it. Those are my states. I will have 2 states, but I need to use 2 bits. Is this clear? Right. Same for traffic lights. I will not have all possible cases, right? Because I don't need all lights to be on at the same time. I don't need green and red to be on and the other one off at the same time. No. So usually we need one of them to be on at a time, not all of them, or 2 of them are on at the same time, and so on. So this is the first thing that you need to do, to find out how many states you have. What are your states? And then the next step is to draw what we call the state diagram. The state diagram will show the transitions. So if we are here now in state 0, 0, the next state should be 0, 1. And when this happens, so you show with arrows. So I will show you in the next slide, or the next 2 slides, I will explain the state diagram. So this is something new to you. So the next step in designing a finite state machine is to get your state diagram. And then next is to set up the system, is to find out the excitation table using D or JK, depending on which flip-flop you choose to use, or the one that you get in your question. So we may ask you to use D flip-flop, we might ask you to use JK. And then once you do the excitation table, we will use it as a truth table to find out the logic, the combinatorial logic. And the combinatorial logic, so we will try to find what is D as a function of Q. So it's not finding what is Q as a function of D. Do you understand? So it's the opposite now. As the excitation table, we'll just inverse the inputs and outputs, right? So we'll try to find what is D or what is J and K as a function of the Q and the other inputs that we may have in a system. If you have a reset, and by the way, so far we didn't talk about clock, right? Clock it's you know automatically there because we are using flip-flop. The clock is there. We don't even mention it in the the state diagram. Now I'm going to explain the state diagram, and then I will give you an example. We'll finish with an example. Right. The first thing that, as you can see here in the state diagram, we use circles and the value of the state. Here, basically, we put the output. So let's say I have two states, state 1 and state 2. Of course, I put here the value 0, 1, for example, or if 2 bits, I put 0, 0, 0, 1, for example, and so on. So here, we inside the circle, we put the value of the output. And then we say, and then we need to show the link between the states. We use arrows. So here I say, if I am in state 1, I can go to, so the next possible state is state 2. So if I am in state 1, the next possible state is state 2. And here we can put the transition condition. So it could be if we have an input in our circuit, a control line or whatever. If A is 0, if A is 0 and you are in this state, then you can go to state 2. And then if you are in state 2 and then A is 1, you can go to the state 1, back to state 1, and so on. So this is a simple state diagram that shows two states and arrows that shows the transition between them. This is what we use in state diagram. One state could have multiple next states, so it doesn't need to be only one state as the next state. So it could have, for example, here state 2. The next state could be state 3. It could be state 4. This will depend on the condition here. And the condition, it will be based on the other inputs of your circuit. The next state could be the same state itself. So state 2 has 3 possible next states. So it could be the same state itself. It could be state 3. It could be state 4. Is this clear? So, and again, this will be based on the condition. So an example of same state, let's say that we are in state 0, 0, and then it's a counter. And this counter doesn't have any other inputs, just clock that goes through all flip-flops, and then the outputs, 2 bits. And then it has a reset, just a reset. So next state could be 0, 1. When do we go from one state? Of course, this test will happen every clock cycle. So every clock cycle, if we are here, we go to next state, 0, 1. But if there is a reset, if reset is 1, if reset is 1, we stay here, right? 0, 0. So the next state could be 0, 0 if there is a reset, or it could be 0, 1 if there is nothing and there is no condition here. So here, this means rising edge. Every rising edge, we go to the next state. Right. Let's do a simple example, and we'll finish with this. And then, of course, we will do more in the next session. Suppose that we wish to design a synchronous system that will leave an output unaltered after a control line is set to 1. So we have a control line in our circuit. So if this control line is 1, then the output will remain as it is. If this control line is 0, then the output will be the opposite of the current one. The next output will be the opposite of the current one. So basically, it's like we will have a circuit that has one output. If I call it Q, and then it has one input A. And this is what I want to design. This is my finite state machine. So I want to know what will they have here. So definitely, because I have one output, I will need one flip-flop. So I'm going to use, let's say, D flip-flop in this example. It's one output, so I'm going to use one flip-flop. So I know before starting my design that I will need one flip-flop to be here. The flip-flop will have D, will have clock, will have Q, and will have Q bar. This will need to be used in this circuit. And then I know that my circuit will have an input A according to this description. There is an input A. Is this clear so far? So I have a circuit. This is what we want to do. I have a circuit, a finite state machine that I want to design. I know it has one output. Let's call it O. I'm not going to use Q so it doesn't confuse. And it has A input. We say if A is 0, output O is equal not O. So On plus 1 is equal not On, not the current one, right? If A is 1, On plus 1 is equal On. We say it stays as it was, no change. So this is what I want to design. This is what we have in the description. Right, I know I have one output, so I have 0 or 1. So I need just one flip-flop. So in this circuit, I need one flip-flop. Let's use a D flip-flop, and I can solve the problem with the JK flip-flop if I want. So let's start with the simplest case. So this is Q, this is clock, and we have Q bar. That's it. So this we need to be here. Now the question is, how am I going to connect this? How am I going to connect Q, D, clock? How about A? So I have A as well in my circuit. So A is here. What should I do here? And this is what I mean by the excitation tables. So we need to find the logic here to connect A. So this D, and I may need to use the Q and Q bar back here to be connected to D. So D will be a function of A, Q, and Q bar. This is what I need to find. So the first step is to do the state diagram. So I know I have two possible states, 0 or 1. This is very simple, right? I know that the outputs that I can have, it's either 0 or 1. Now, if I am in this state 0, and then I have A is equal 0, then I will go to state 1. If A is equal 0, and the current state is 0, the next state should be 1. If I am in state 1, and A is 0, then the next state should be 0. Now, if I am in this state and A is 1, then there is no change, right? Same here. Then there is no change. I think this is very simple state diagram. We have two cases, 0 and 1, and we show the transition, when the transition will happen between the states. Is this clear so far?
Yep. Yes.
So we have two states, two possible outputs, 0 or 1, and then depending on A. And this is how I use them in a state diagram. This is how I draw it in state diagram. Right. Next, I will use the state diagram to get my excitation table. In my excitation table, I should, in addition to the Qs, which I put here, I should include the other inputs, all other inputs that I might have in my circuit. In my circuit, I have only A. And then the output will be Dn. I'm going to use now the excitation table of the D flip-flop, saying that, okay, now if my Q is 0, so I'm here, if Q is 0 and A is 0, I know that the next state should be what? Should be 1. I'm using my excitation table, right? So Q is 0. and A is 0. So according to this, state diagram, Q, the next Q should be 1. How do I guess the next Q should be 1? By putting D is equal 1. And then I go to the next case. Now, if I am here, Q is 0 and A is 1, the next state should be 0, so I should stay here. So what should I do on D to get the next state to be 0? I will just put D is equal 0. You know, using the D flip-flop, it's easy because D is equal Q, the next Q. So whatever I want next, I will just put it as the value of D. And next, if I am in state 1, Q is 1, and then A is 0, then I should go to state 0. Q should be 0. Then I need to put D is equal 0. And then the last one, 1, 1, I will get 1. I need to have D1 to force it to be 1 because I will need to stay here in this state. Is this clear? How did they get this excitation? Those are just comments, but I think you cannot read them, so you can read them on the. I'm just explaining in text what I've just said. Is this clear? What do I need to do next? I will use this table as like a truth table, and I will try to find what is D. So what is D as a function of Q and A? What is D here?
Q bar A bar plus QA.
Yeah, what is the what is this? So it's Q bar A bar plus Q bar I, and this is a X naught. Just for you can do the K-map if you want, or I think this case is very simple. So this is what we get. So it's just an X naught. So D0 is equal Q0 X naught A. Here, as you can see, we are not using Q0. And then I will just need to draw the circuit. So now I found D0. So I know that I have a D flip-flop. I need a D flip-flop. Q is the output that goes to, this is my O. So this is my output. And then this is how I connect the D. So when you design finite state machines, you need to find out how to connect your Ds and your JKs if you have multiple JK flip-flops or you have multiple D flip-flops. So this is the task. Now, D0 is equal A. So this is the input A of my circuit. X nor Q0. Now, you can just put whatever you want on A, assuming that this is a reset 0, and then you will get what we want. So if A is 0, the Q0 will be the opposite of what it was before. If A is 1, the Q0 will be the current. It will stay as it was. Is this clear?
Yeah.
And I advise you to, if it's not clear, to try to, listen again to the recording. And if you have questions, you can ask them later, because this is what we are going to use as well in the next lecture. And by the way, this is the last slide here. So we'll use it again in the next lecture, and then we'll do tutorials. Now, if I want to, now I want to use a JK flip-flop instead of a D flip-flop to solve this this exercise. So I want to replace this with a JK. So basically we will have Q, we will have Q bar, we will have J, and we will have K. So my excitation table will change now. So we need to have J and K here. And now I need to find what is J as a function of A and Q, and what is K as a function of A and Q. And then I can draw it here, connect them. So I may not need this one. I will get a different circuit. And now I'm going to use the excitation table for JK. Now, if I have 0, 0, now I am in 0, and I want the next, and A is 0, the next state should be 1. So I go to the excitation table of the JK flip-flop. Do you remember? We did it, right? Then I will check it. So 0, so current Q is 0, and I want the next Q to be 1. And we have it in the, so what should we do on JK? So 0, and next one is 1. If you go to the truth table, you will see it is 1x. Now, 0, 1, which means I am in this state, and I will stay in this state. So then the current state is 0, and I want the next state to be 0.
0x.
Excitation table is 0x. Good. Now the next state is 1. Next state is, oh sorry, the current state is 1, and the next state will be, for this case, what should be the next state? Should be
0.
0. So 1, and I want to get 0, so it should be x1. If you go to the excitation table, it's x1. And last one, I'm 1, and I stay in 1, so it's x0. So 1, I am here, and A is 1, so I will stay in 1. By the way, you can add to this table, just to avoid confusion, you can add what should be the next Qn plus 1. I'm using this one to get them, yeah? So I can have them in the table if you want. Next Qn plus 1. So 0, 0, the next one, it should be 1. 0, 1, the next one should be 0. 1, 0, the next one should be 0, and 1, 1, next one should be 1. So this is what we need. Now, 0, I want 1. 0, I want 0. 1, I want 0, and then 1, I want 1. And this is what I'm using to get J and K, right? And that's it. Now, those x's, sorry?
I didn't understand this last part. Isn't Qn plus 1 just A?
Oh, no. It's not A. It has nothing to do with A. It has nothing to do with A. Look, I'm here. Okay, tell me. Look, this case. Q is 1. Right?
Yeah.
You follow, yeah? Q is 1. Or let's take this case. Q is 0. And A is 0. Q is 0 and A is 0. What will be the next
So Qn plus 1 becomes 1. Yeah, now I get it. Thank you.
A has nothing to do with the next. It's not has nothing to do. It will affect, of course, what will be the output, but they are not the same. A is an input in our circuit, and it will affect the next case. And we should include it in the excitation table. But again, here I didn't put Qn plus 1, which you could add to the excitation table. If this will help you, I mean, you can add another column here. You put Qn plus 1, and what should be Qn plus 1 based on those cases? I didn't put it because I was using this state diagram. Now I have x's. Those x's, you can replace them with the zeros and ones, whichever will give you the best logic. Do you understand? And then you can guess the J and K. Is this clear?
Yes, doctor.
So here I put X. This X will be replaced with a 0 or 1, whatever can give you the best logic. Okay, that's it for this lecture. Of course, we will continue in the next topic. We will have more complex examples. So I showed you a simple example here where we use D flip-flop, and then we use JK flip-flop. We will do more examples later on.